Welcome to Robots That Adapt, the next leap in AI and robotics. Today's episode explores the latest in adaptive intelligent robotics, drawing insights from 10 cutting-edge research papers published on October 12, 2025. We'll examine real-world impacts as robots become safer, smarter partners, bridging artificial intelligence, perception, and embodied action. Join us as we unpack the breakthroughs shaping the future of robotics. Here is what to expect in this presentation. We will embark on a journey from foundational robotics to the newest frontiers, highlighting 3 dominant research themes that define the field. The discussion will delve into technical innovations and tangible real-world impacts, while spotlighting seminal papers that are shaping the landscape of robotics research. The session concludes with a synthesis of future directions and the methodological approach behind this review. Let's begin with a field overview. Robotics and computer science is an interdisciplinary domain that blends hardware, software, and intelligence. The focus lies in perception, decision-making, and control, enabling applications across healthcare, manufacturing, and exploration. The field is rapidly evolving, driven by advances in artificial intelligence and sensor technology. Progress depends on collaboration across mechanical and electrical engineering, as well as computer science, reflecting the multifaceted nature of robotics. The first major theme is learning-based control in robotics. Modern robots are no longer limited to rigid, pre-programmed behaviors. Instead, they learn from experience. Notably, Tingxuan Leng and colleagues have demonstrated how humanoid robots can blend precise command following with compliance to external forces, making robots more adaptable in human environments. Alexander Langman's work focuses on balancing multiple objectives within control frameworks. Reinforcement learning underpins these advances, enabling robots to perform adaptive, nuanced actions. The core concept is to position robots as flexible, context-aware partners rather than mere automatons. The second theme centers on enhanced robot perception. Recent advancements in sensor technology have expanded robots' ability to perceive challenging environments. David Rodriguez Martinez and collaborators utilize single-photon imaging to support planetary navigation, enabling robots to operate in near darkness. Zhuoheng Gao's team leverages brain-inspired spiking neural networks to detect optimal grasps for manipulation, even in cluttered or low-light scenarios. Kush Garg and colleagues employ LiDAR systems for non-line-of-sight mapping, giving robots the ability to perceive spaces that are not directly visible. The technical focus here is on spiking neural networks, which provide energy-efficient, event-driven processing inspired by biological systems. The third theme involves advances in simulation, energy efficiency, and adaptive behavior. Haoyu Zhao and team introduce high-fidelity simulators that narrow the gap between virtual training and real-world deployment. Kanishka Jaisankar's research centers on spiking neural networks that serve as energy-efficient control architectures for robotic systems. The concept of sim-to-real transfer allows robots to be trained in virtual environments and then deployed in reality with minimal adjustment. Jared Grinberg's work on advanced sensing improves dexterity and safety in legged robots. Technically, population coding is emphasized, encoding information using groups of neurons, which enhances robustness and adaptability. Key findings from these studies are transforming robotics research. Robots can now blend command following with real-time adaptation, as demonstrated by Tingxuan Leng's team. Simulation frameworks like those introduced by Haoyu Zhao enable zero-shot deployment, allowing policies trained in virtual environments to succeed in the real world without further tuning. Kanishka Jaisankar's population-coded spiking networks have reduced energy usage by 96% while maintaining high performance. Kush Garg's implementation of single-photon sensors and LiDAR expands robotic perception beyond direct sight, and Zhuoheng Gao's spiking grasp detection systems overcome challenges posed by cluttered or poorly lit settings. How are these breakthroughs achieved? Methodologically, reinforcement learning is a cornerstone, allowing robots to learn optimized behaviors through trial and error. Spiking neural networks provide brain-inspired, energy-saving computation, well-suited for both perception and control. High-fidelity simulation, featuring photorealistic graphics and accurate physics, allows for scalable training and validation, automated asset generation. Using advances in artificial intelligence streamlines the creation of virtual training environments. Sensor fusion, which combines data from multiple sensing modalities, grants robots precise awareness of contact and improved perception in complex scenarios. The first highlighted paper is by Tingxuan Leng and colleagues, entitled Preference-Conditioned Multi-Objective Reinforcement Learning for Deployable Humanoid Locomotion. This work addresses the challenge of balancing command following and compliance in humanoid robots. The authors introduce a preference-conditioned reinforcement learning framework, enabling robots to blend and switch behaviors in real time according to situational demands. The approach demonstrates faster convergence, robust adaptation, and is deployable on real-world humanoid robots. This paper is recognized for its significant impact on safe and collaborative human-robot interaction. The next seminal contribution comes from Haoyu Zhao and collaborators, titled RoboSimGS, Photorealistic Simulation for Zero-Shot Robotic Manipulation. This work presents the real-to-sim-to-real pipeline, which supports scalable robot learning by automating asset creation through language and vision models. Policies are trained entirely in simulation and can be deployed in reality without additional tuning, significantly boosting performance and generalization for manipulation tasks. This framework is chosen for its revolutionary impact on scalable robot training and its ability to accelerate innovation across multiple robotic domains. Kanishka J. Sankar and colleagues contribute a key advancement with their work on population-coded spiking networks for robotic control. Their research demonstrates how population-coded spiking neural networks can tackle complex robotic tasks while drastically reducing power consumption. Gradient-based reinforcement learning is applied on the Isaac GYM platform, resulting in high-performance control policies that can run on modest hardware. This approach enables mobile robots to achieve advanced control without significant energy costs, thus bridging the gap between computational power, intelligence, and scalability. Looking forward, several future directions emerge for robotics. Multi-objective, adaptive control strategies are expected to facilitate more collaborative and context-aware robot partners. The automation and democratization of simulation asset creation will make high-fidelity virtual environments accessible to a broader research community. Advances in non-line-of-sight perception and brain-inspired computation will further expand robotic capabilities. Ongoing challenges remain, including generalization across tasks and environments, sensor fusion complexities, and the interpretability of deep neural network decisions. The importance of safety, ethics, and effective human-robot interaction will continue to grow as robots are integrated into everyday life. This deck was synthesized using GPT 4.1 by OpenAI for summarization and narrative construction. Text-to-speech synthesis is provided by OpenAI, with supporting image generation by Google. Human experts reviewed the content for both clarity and technical accuracy, though minor inaccuracies may remain. All research references are provided to ensure a balanced and comprehensive overview of recent advancements. To stay informed on the latest in AI and robotics, subscribe to our YouTube channel. Here, you will find updates on breakthroughs, expert insights, and a community passionate about the future of intelligent machines. Your feedback is vital and helps shape future episodes, so please share your thoughts. Thank you for joining us as we continue to explore the frontiers of robotics and artificial intelligence.